So let's consider p-value a little bit more. A statistics instructor gave a coin to each of two students. The two students wanted to test whether their coins were fair. So they flipped their coins many times and recorded the proportions of heads facing up. What are the hypotheses for each of the students in symbols? All right. So let's think about this. When we look at a coin and we want to determine whether it's fair, right? We want to look at the proportion of heads, right? So if it's a fair coin, this heads will show up 50% of the time. So this is a Hong Kong dollars from 1975, by the way. So defunct currency, it doesn't work anymore. Okay, so let's write this. So it'll be proportions because it's a coin. And then if it's fair, the heads will come up 50% of the time. So 0.50. Right, so this would mean in words, which I didn't ask for, but I'll write down right here. Coin is fair. Right, a fair coin is not like a fair game, but a fair coin means that both sides are equally likely. All right, so if it's not fair, that means it could show up tails a lot more often or heads a lot more often. So to be that the p is not equal to 0.5, it's a two-tailed test, because we're not saying which side we think is going to show up more often. We're just saying that's not going to be 50-50. All right, so there's symbols, there's words. Sorry, so symbols, sorry, is over here. Words is over there. Not because it asked for it, but sometimes I do ask for words and symbols. So there you go. That's what you write. Okay. The students collected their data and each ran a hypothesis test. The test statistic for student A was 1.8 and the test statistic for student B was negative 2.1. Which of these test statistics has the smaller p-value? Explain. Okay, so I'm going to draw two pictures. I'm going to try to draw them one right over the other so we can kind of look at these. There we go, I didn't do too badly. So this will be student A, this will be student B. Okay, so student A has a test statistic of 1.8. So let me do that in orange here. So 1.8 would be, well, we know that right there at the inflection point's 1-ish. So we're going to go a little bit further. So 1.8. So there's 1.8. And then there's a counterpart because it's a two-tailed test. So there's negative 1.8. The p-value is the area in both of the tails. Similarly, for the two-tailed test, for student B, it's negative 2.1. So if this is negative 1.8, 2.1 is a little bit further away. So this is negative 2.1, and then we have to have a companion over on the other side. So positive 2.1. And then these tails right here. And the p-value for student B is the area in both of those tails. So the question is, which of these tests has the smaller p-value? Which one has the smaller area shaded in the tails? And the answer is student B, right? Student B has the smaller p-value. Why? It's because their z-score of negative 2.1 is farther away from 0. Remember that down the middle of both of these curves is 0. So 2.1 is farther away from 0, the mean. So the area in the tails is smaller. Now let's think about a couple other things here. If you have a smaller p-value, think about what that means, right? If the lower your p-value, that means that your results are more significant. So student B, this is just a note over here. Student B has a lower p-value. Now what is that going to imply? That leads to they have a more statistically significant result, right? The lower your p-value, the more statistically significant. Right? That also means that you're more likely to reject HO, right? Because more statistical significance means more rejecting of HO, the null hypothesis. And that in turn means that we have the better result, right? Student B has the better result, right? The lower your p-value, the more significant it is. I cannot stress this enough, right? Lower p-value means more significant. They go together. All right, now this leads us to a comment that we want to make, right? Something else we want to make a note of, right? Since your p-value is the area in your tails, that means that the farther your p-value is, or excuse me, your z0 is from 0. Let me draw a picture real quick. I'll draw it over here, right? So here's your normal curve. 0 is always in the middle. So you have your negative z0 over here, your positive z0 over here. It doesn't really matter if it's two-tailed or not, but the two-tailed picture is the easier one to kind of imagine, right? Your p-value is the area in both of those tails, right? What it just wrote here. I didn't have to write that. It was right there. All right, so the p-value is that area in those tails. So the farther the z0 is from the mean, which is 0, right? The mean is always 0. It's in the center. So the farther z0 is from the mean, which is 0, the smaller the p-value would be. And therefore, the more significant the result. It's more statistically significant, I should say. Nice. All right, so that's key. Right, you want to make a strong note of that, right? Your z0s being larger make it farther from the mean. The farther it is from the mean, the smaller the p-value. Okay, so let's think about what if the p-value that StatCrunch gives you is annoying. So a lot of times you'll see this when you go to StatCrunch. I'm just going to give you this box. Like that's what it's going to give you. It'll just look like that at the end of your StatCrunch. And be like, what in the world? All right, so why do we not have an actual number? Like what in the world is going on? And the answer is basically that StatCrunch limits how many decimal places, literally how many digits it will allow in the program. And so once you go past that number of digits, it won't give it to you anymore. StatCrunch does this, but actually a lot of computer programs do this. So let me just write the computer program, or if you run, you could write StatCrunch, but it's not just StatCrunch. Lots of programs do this. The computer program is restricting the number of digits, right? Essentially, it's going to allow 1, 2, 3, 4, 5, 6 characters, and that's it. So it's restricting the number of digits. It technically is the number of characters, but that's fine. The number of digits, right? And then possible. So the number of, I'll just say that. It's restricting the number of digits. It's not going to tell you the p-value, right? So we have to think about what it means then. So it's restricting the number of digits possible. I'll just say that. Let's just leave it that way. So what's going on then? Like what's happening? Well, the answer is what's happening is this p-value is actually really, 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 really little, right? This little symbol right here means less than. So they're telling you, hey, we're not going to give you the p-value because it's just got too many zeros in it. So I guess that's the thing I want to say. So the computer program is restricting the number of digits. There's lots of zeros. Lots more zeros than what we see. So for example, it's 0.000000008. That it's not going to do that. It's too many zeros. It's going to restrict. It's like, nope, I don't want to write anything with that many zeros in it. So it's saying instead it's less than 0.00001, which this is, right? This value is smaller than that. Okay, so hopefully that makes sense. Computer programs have very strict limits sometimes, just in space, and they don't want to write it, so they just kind of say, you don't need to know what it is, right? It's something like this. You don't need to know that. All you need to know is that whatever it is smaller than 0.00001. So the question for you then is that p-value, even though you don't know what it is it statistically significant? In other words, do we get to reject HO, right? Because statistically significant is code for do we get to reject the null hypothesis or not? And the answer is sure, of course we do. Like, we don't know what it is, but we know it's really, really small, right? So that p-value, which is smaller than 0.0001, is definitely less than my alpha, which is 0.01. So yes, we reject HO. Right? Your p-value is really small. Really, really, really small. It's something like what you see here. And therefore, even though we don't know exactly what it is, we know that it's smaller than 0.01, right? Because we know it has lots of zeros on it. It has at least 3 zeros on it. So 4 zeros, 5 zeros, 7 zeros, and however many zeros it has, it is smaller than 0.01. So we're going to reject HO because this is less than alpha.